Hi folks, we're going to take a look at page 575, number 13. So here they give us this function. The first thing they want us to do is to determine the derivative, and then they want us to find the domains of both the original function and the derivative function. All right, so let's start by taking the derivative here. So we're going to have to use the chain rule here because I've got ln of some function of x, so we've got a composite function. So let this be my u. So step one is to take the derivative of ln u, which is just 1 over u. So 1 over ln x, and then we have to multiply that by the derivative of u with respect to x. And so the derivative of ln x is just 1 over x. Okay, and then we can, just write that as 1 over x ln x. All right. So there's the derivative. Let's take a look at the domains here. So if we take a look at the original function, y equals ln of ln x, so we have to remember what it means to be in the domain of a composite function. Okay, it's a two-step process. So x has to be in the domain of the interior function. So it has to be in the domain of ln x. Okay, so we know that the domain of, ln x, x is just going to be x greater than 0. Okay, it's only defined for values greater than 0. But then the second part of that is the outputs of ln x have to be in the domain of the outside function, which is yet again ln x. So what I'm going to do is I'm going to do this graphically. I'm going to graph the interior function. Okay, ln x we know looks something like that. And I'm only going to take those values whose outputs are in the domain of the second function. So again, what do you need to be? In order to be in the domain of the second function, you need to be greater than 0. So I'm only going to take outputs that are greater than 0, and those occur once we're past x equals 1. Okay, so the domain of ln x, okay, is I'm only going to take those values in the domain of ln x whose outputs are greater than 0. So in other words, it's going to be all values greater than 1. So I'll write it in interval notation. Okay, so just keep in mind that when you're finding the domain of a composite function, you have to not only determine what x values are in the domain of the inside function, you also have to determine which of those outputs are going to be in the domain of the second function, the outside function. In this case here, only those that are greater than 1. All right, so let's take a look at the derivative. So the derivative is this function here. Now, if we take it just as its own function, we can find that domain. But of course, if we're using this as the derivative of the original function, I'd be only interested in values of x greater than 1. But let's find the domain of this function as it is. So here again, we see that we have x has to be greater than 0. Okay, because ln x is not defined for anything greater than 0, but we also have to eliminate anything that makes the denominator 0 because I've got a quotient here. So here, obviously, x can't be equal to 0. That would make the denominator 0, but that's already been excluded by virtue of the ln x. But here's where we have to be careful, is when is ln x equal to 0? Well, ln x is equal to 0 when x is equal to 1. So we also have to exclude x equals 1. So the domain of this function, 1 over x ln x, is going to be given by, and this time I'll write it in set notation. Okay, so x can be any real number such that, well, x has to be greater than 0, but x can't be equal to 1. Okay? And there's my domain. So just to recap here, in part 1, it was just using the chain rule on the function here, as we've done many times. And then in part B, the main thing I would say in that first part, when we determine the domain of the original function, is to remember how to determine the domain of a composite function. So step 1 is x has to be in the domain of the interior function, and then those outputs need to be in the domain of the exterior function. All right, that's it for this one.